A star like ours might be the only kind that can host complex life.
That's right, and it flips everything we thought about alien worlds on its head. For decades, astronomers focused on red dwarf stars because they make up about 75% of all stars in the universe. They're small, dim, and incredibly long-lived. Some could shine for trillions of years. So naturally, we assumed if life exists elsewhere, it's probably orbiting one of those. But new research suggests that assumption might be dead wrong. In fact, it's possible that red dwarfs are cosmic dead ends for anything more complex than microbes, if even that.
Wait, so you're saying most of the galaxy is basically a lifeless desert?
Not entirely lifeless, but likely hostile to complex life. The key insight comes from astrophysicist David Kipping at Columbia University. He tackled what's known as the red sky paradox, a puzzle that's been nagging scientists for years. If red dwarfs dominate the galaxy, why do we live around a sun-like star? Shouldn't we be the exception, not the rule? Kipping used Bayesian statistics, a method that updates probabilities as new evidence comes in, to test two competing ideas. 1. Red dwarfs can support life just fine, and we're just lucky. 2. Red dwarfs are fundamentally bad for complex life, and that's why we're not orbiting one. His conclusion? The second scenario is overwhelmingly more likely.
Okay, so what's so bad about red dwarfs? I've heard they're stable and long-lasting. Shouldn't that give life more time to evolve?
On the surface, yes, it sounds perfect, but the reality is brutal. Red dwarfs are notorious for violent stellar flares. We're not talking about occasional solar flares like we get from the sun. These are super flares, hundreds or even thousands of times more powerful, erupting multiple times per day. Planets in the so-called habitable zone of a red dwarf have to orbit extremely close to stay warm, often closer than Mercury is to our sun. That proximity puts them directly in the line of fire. These flares blast planets with X-rays and extreme ultraviolet radiation, enough to strip away atmospheres over time. Without a thick, protective atmosphere, liquid water can't survive on the surface, and complex life as we know it can't exist. And it gets worse. Many red dwarf planets are likely tidally locked. One side permanently faces the star, the other is in eternal darkness. That creates extreme temperature differences, potentially driving supersonic winds and making stable climate zones rare. Plus, the early life of a red dwarf is especially violent. During its first billion years, it's in a hyperactive flare phase, which could sterilize any emerging biosphere before it even gets started. So even if a planet forms with oceans and organic molecules, it might never get past the microbial stage.
That's bleak. But hold on, if red dwarfs are so hostile, why have we found so many Earth-sized planets around them? TRAPPIST-1 alone has 7.
Great question, and it's exactly why this is so tricky. We found so many because red dwarf systems are easy to study. Their small size and low brightness make planetary transits, when a planet passes in front of the star, much more detectable. Also, because habitable zone planets orbit so closely, they transit frequently, giving us more data faster. So it's not that red dwarfs are better at making Earth-like worlds, it's that they're easier for us to observe. It's a selection bias, not a sign of abundance. In fact, Kipping argues that this observational convenience has misled us into overestimating their potential.
So what does make a star good for life? Is it just being sun-like?
According to Kipping's analysis, there's a Goldilocks mass range for stars, between 0.74 and 1.6 times the mass of our Sun. Stars in this range, mostly G-types like ours, and some K-types, live long enough for complex life to evolve, but not so long that they delay the emergence of intelligence. They're stable, with far fewer destructive flares. Their habitable zones are far enough out that planets aren't tidally locked and can retain atmospheres. And crucially, they provide consistent energy over billions of years, just like our sun did for Earth. This narrow window, he argues, is where life is most likely to arise. And here's the kicker. These stars make up only 10% of all stars in the galaxy.
Only 10%? So we're not just lucky, we're in the cosmic minority.
Exactly. And that's the core of what Kipping calls solar hegemony, the idea that sun-like stars aren't just common hosts for life, they might be the only viable hosts for complex, multicellular, or intelligent life. It's a radical shift. For years, we assumed life would be everywhere, especially around the most numerous stars. But if Kipping is right, the universe might be filled with sterile red dwarf systems, trillions of planets, but no forests, no animals, no civilizations. Just quiet, irradiated rocks under crimson skies.
That's honestly kind of lonely, but also fascinating. So if red dwarfs are out, where should we be looking next?
That's where things get exciting, and that's exactly what we'll dive into next. Because if sun-like stars are the true cradles of life, then our search strategy needs a complete overhaul. We'll explore which nearby stars fit Kipping's criteria, what missions are already targeting them, and whether Earth's timeline, life emerging early in cosmic history, is another clue that we're not random at all.
So if red dwarfs are such hostile environments, how did we even get to this conclusion? I mean, we can't exactly send a probe to TRAPPIST-1 yet.
Great question. And the answer lies in a combination of cutting-edge telescopes, decades of stellar observations, and clever statistical modeling. It all started with the Kepler Space Telescope, which revolutionized exoplanet science by staring at a single patch of sky for years, watching for tiny dips in starlight caused by planets crossing in front of their stars. Because red dwarf systems are so compact, those transits happen frequently and are easier to detect. That's why early catalogs were flooded with Earth-sized planets around N-dwarfs. But detection is one thing. Habitability is another. Scientists soon realized that just because a planet is the right size and in the habitable zone doesn't mean it's actually livable. That's when attention shifted to the stars themselves.
Right, so we started studying the stars more closely.
Exactly. Missions like NASA's TESS, Transiting Exoplanet Survey Satellite, and ESA's KEOPS began monitoring red dwarfs not just for planets, but for stellar activity. And what they found was alarming. Using ultraviolet and X-ray instruments, especially from the Hubble Space Telescope and the Chandra X-ray Observatory, researchers documented that many red dwarfs emit superflares multiple times per day. For example, Proxima Centauri, the closest star to us, and a red dwarf, blasted its planet Proxima b with a flare so powerful in 2016 that it briefly outshone the star in UV light by a factor of 14,000. That single event likely stripped away a significant chunk of the planet's atmosphere, if it even had one to begin with. And it's not just flares. Red dwarfs also have intense magnetic fields that drive constant coronal mass ejections, huge bubbles of magnetized plasma hurled into space. On Earth, our magnetic field and thick atmosphere shield us from solar storms. But a planet orbiting a red dwarf at 0.03 AU, typical for the habitable zone, would be bombarded relentlessly. Over time, that radiation erodes atmospheres, especially lighter molecules like water vapor and oxygen. Without atmospheric pressure, liquid water boils away, even at low temperatures. In fact, models from the University of Chicago and the Max Planck Institute show that under sustained XUV, extreme ultraviolet radiation, an Earth-like atmosphere around a red dwarf could be stripped in under 100 million years, far too fast for complex life to evolve.
But wait, what about planets with strong magnetic fields of their own? Couldn't that protect them?
That's a common hope, but here's the catch. To generate a protective magnetosphere, a planet needs a molten iron core and rapid rotation. Yet most red dwarf planets are likely tidally locked, meaning one side always faces the star, the other is in a perpetual night. Tidal locking dramatically slows a planet's rotation, possibly to the point where it can't sustain a global magnetodynamo. Even if it did, the intense stellar wind from the star would compress the magnetosphere on the day side, leaving the atmosphere vulnerable at the poles. And there's another problem. The intense radiation may prevent the formation of a thick secondary atmosphere in the first place. On Earth, volcanoes and biological processes replenished our atmosphere over billions of years. But if a red dwarf sterilizes the surface early on, those processes might never kick in. Then there's the issue of water. Many red dwarf planets may have formed farther out and migrated inward, meaning they could be water-rich. But during the star's violent youth, its first 500 to a billion years, it's in a saturation phase of extreme activity. Any water on the surface would be broken apart by UV radiation into hydrogen and oxygen. The lightweight hydrogen escapes to space, while oxygen either reacts with surface rocks or builds up in toxic concentrations. We've actually seen this in action. Observations of the TRAPPIST-1 system by the James Webb Space Telescope in 2024 found no signs of water vapor in the atmospheres of its inner planets, despite them being in the habitable zone. That suggests they're dry, irradiated worlds.
So even if life somehow started, it wouldn't survive long enough to become complex?
Precisely. Microbial life might cling on in subsurface oceans, like on Europa or Enceladus. But complex multicellular life needs stable surface conditions over hundreds of millions of years. Think about Earth. It took about 4 billion years for intelligence to emerge. That required a stable climate, liquid oceans, a protective ozone layer, and consistent energy from the sun. Red dwarfs simply don't provide that stability. Their habitable zones shift dramatically as the star ages, and their flares create wildly fluctuating radiation environments. It's like trying to grow a rainforest in a lightning storm. And this is where David Kipping's statistical approach becomes so powerful. He didn't just look at individual systems, he asked a bigger question. Given that we exist, what does that tell us about which stars are truly capable of hosting observers like us? Using Bayesian inference, he compared two hypotheses. Hypothesis A, all stars are equally likely to host complex life, so our sun-like system is just a fluke. Hypothesis B, only stars in a narrow mass range can support complex life, so our existence isn't random, it's expected. The data overwhelmingly favored hypothesis B. In fact, Kipping calculated that the odds of us living around a sun-like star by pure chance, while red dwarfs dominate the galaxy, are less than 1 in 10,000. That's not luck. That's evidence.
So our very existence is a clue about the universe's rules for life.
Exactly. It's a form of cosmic self-selection. If complex life can only arise around certain stars, then any civilization that asks, "Why are we here?" will always find itself orbiting one of those rare, favorable stars, even if they're only 10% of the total. That resolves the red sky paradox. We don't see a red sky because red dwarf systems don't produce observers. It's not that life is impossible there. It's that it never gets past the microbial stage. And that has huge implications for where we should focus our search.
Which brings us back to your earlier point. Maybe we've been looking in the wrong places all along.
Absolutely. For years, SETI and exoplanet missions prioritized red dwarfs because they're numerous and easy to study. But if Kipping is right, we've been chasing ghosts. The real action is around G and K-type stars, stars like Tau Ceti, Epsilon Eridani, or 82 Eridani. These are stable, long-lived, and offer wide, calm, habitable zones. Upcoming missions like NASA's Habitable Worlds Observatory, scheduled for the late 2030s, are being designed specifically to image Earth-like planets around these stars. And here's the kicker. Preliminary data from Gaia and TESS already suggest there are hundreds of Sun-like stars within 100 light-years that could host Earth 2.0.
Hundreds? That's still a lot of targets, but how do we know which ones are truly promising?
That's the next frontier, and it's where things get even more fascinating. Because it's not just about the star's mass. It's about timing, metallicity, galactic location, and even the presence of Jupiter-like planets to deflect comets. And that's exactly what we'll unpack next, the hidden checklist that makes a star system not just habitable, but optimized for life like ours.
So if red dwarfs are basically cosmic dead ends for complex life, that means we've been looking in the wrong places for decades. But hold on, what about all those Earth-sized planets we found? Doesn't that still count for something?
It's a great point, and it cuts right to the heart of the observational bias problem. Yes, we've found thousands of Earth-sized planets, but size and location in the habitable zone are just the first filters. They don't guarantee habitability. Think of it like real estate. Just because a house is in a nice neighborhood doesn't mean it has running water, electricity, or a roof that won't collapse. In fact, many of these planets may be what astronomers call desiccated worlds, dry, airless rocks baked by relentless radiation. The James Webb Space Telescope has already started testing this. In 2024, JWST observed the atmospheres, or lack thereof, of planets in the TRAPPIST-1 system. Despite being Earth-sized and in the habitable zone, none showed signs of water vapor, CO2, or other biosignature gases. That's a huge red flag. And here's another layer. Even if a red dwarf planet somehow retained an atmosphere, its chemistry would be unlike anything on Earth. Because these stars emit most of their light in the infrared, photosynthesis as we know it might not work. Plants on Earth rely on visible light, especially red and blue wavelengths, to power sugar production. But under a red dwarf's dim crimson glow, the energy per photon is lower. Some scientists have modeled alternative biochemistries, like using infrared photons or even geothermal energy, but these are highly speculative. There's zero evidence that such systems could support complex, multicellular life. Evolution on Earth required billions of years of stable energy input. Red dwarfs simply don't provide that kind of consistency. Then there's the issue of time. Red dwarfs live for trillions of years. But that's actually a problem for the emergence of intelligence. Why? Because if life takes 4 to 5 billion years to produce observers like us, but the star will shine for 10,000 times longer, then statistically, we should be appearing much later in cosmic history. Yet here we are, only 13.8 billion years after the Big Bang, barely into the universe's adolescence. That's the second part of the red sky paradox. Not just why aren't we around a red dwarf, but why did life arise so early? David Kipping argues this isn't a coincidence. If only stars with lifespans of 5 to 15 billion years can produce complex life, then civilizations will always emerge relatively early in the universe's timeline, exactly like us. It's another piece of evidence that red dwarfs, despite their longevity, are evolutionary cul-de-sacs.
Okay, so red dwarfs are out. But what about other types of stars? Are all G and K-type stars automatically good candidates, or are there hidden traps there too?
Excellent question. And this is where the story gets even more nuanced. Not all sun-like stars are created equal. Take metallicity, for example. Stars with very low metal content, meaning few elements heavier than hydrogen and helium, tend to form fewer rocky planets. Our Sun has relatively high metallicity, which likely helped Earth form with a rich inventory of iron, silicon, oxygen, and carbon. Then there's stellar activity.
Even some G-type stars can be flare stars if they're young or rapidly rotating. But crucially, by the time they reach middle age, like our 4.6 billion-year-old sun, they've settled into a calm, stable phase. That stability window is key. Kipping's solar hegemony range of 0.74 to 1.6 solar masses isn't just about mass, it's about the entire life cycle. These stars live long enough for life to evolve, but not so long that they delay the emergence of intelligence. They also have wide habitable zones, reducing tidal locking risk, and emit the right kind of light for Earth-like photosynthesis. And let's not forget galactic location. Stars too close to the galactic center face frequent supernovae and gamma-ray bursts, cosmic sterilization events. Too far out in the galactic suburbs, and there's not enough heavy elements to form rocky planets. Our solar system sits in what's called the galactic habitable zone, a sweet spot about 27,000 light-years from the center. Combine that with our sun's ideal mass, stable output, and protective Jupiter deflecting comets, and you start to see why Earth isn't just lucky, it's optimized. Now, does that mean every star in Kipping's range will have an Earth? No. But it means the probability is orders of magnitude higher than around red dwarfs, and that changes everything for how we search.
So instead of scanning every red dwarf within 50 light-years, we should be laser-focused on sun-like stars, even if there are fewer of them?
Exactly. And the good news is, there are still plenty. The ESA's Gaia mission has mapped over 1 billion stars, and within 100 light-years alone, there are more than 200 G and K-type stars that fit Kipping's criteria. Some are already on astronomers' shortlists. Take 82 Eridani, a K1-type star, just 20 light-years away. It's slightly less massive than the Sun, but stable, metal-rich, and has at least 4 known planets, one of which orbits near the inner edge of the habitable zone. Or Tau Ceti, a G8 star 12 light-years away, with a debris disk suggesting terrestrial planet formation. These systems are now prime targets for next-generation telescopes like the Habitable Worlds Observatory, which will directly image exoplanets and analyze their atmospheres for oxygen, methane, and other biosignatures. But here's the fascinating twist. If Kipping is right, then the absence of signals from red dwarf systems in SETI data isn't a failure, it's confirmation. For decades, SETI has listened to thousands of red dwarfs, hoping to catch a whisper of alien technology. Silence. Now we may know why. There's no one there to whisper. Meanwhile, the few sun-like stars we've monitored, like Vega or Sirius, have also been quiet, but that's partly because we haven't looked deeply enough. Upcoming radio arrays like the Square Kilometer Array will be able to detect Earth-level radio leakage from dozens of nearby G and K stars. If complex life is truly rare and tied to solar hegemony, then the first signal we detect might not come from the most common stars, but from the rarest, most Earth-like ones.
That's a total paradigm shift. We went from life is everywhere to life is rare and only possible in very specific places. But wait, if this is true, does that mean Earth is special or even unique?
That's the million-dollar question, and it's where science meets philosophy. Kipping's work doesn't say Earth is unique, but it does suggest we're part of a small cosmic minority. In a galaxy with 200 billion stars, maybe only 20 billion are even capable of hosting complex life. And of those, only a fraction will have the right planetary conditions, timing, and luck. But rare isn't the same as alone. If just 0.1% of those 20 billion stars have an Earth 2.0, that's still 20 million potentially inhabited worlds. The universe is vast enough that even rare events can happen many times. What's profound is that our existence isn't random, it's a clue. We're not flukes orbiting a typical star. We're observers in a system that was primed for life. And that means when we look for others like us, we shouldn't chase the crowd. We should follow the blueprint.
So the real search begins now, not with red dwarfs, but with stars like ours. But how do we know which ones are truly Earth-like? What's the checklist?
That's the next frontier, and it's more detailed than you might think. It's not just mass and stability. We need to consider planetary system architecture, the presence of gas giants for comet deflection, the star's rotation history, magnetic activity cycles, and even whether it has a binary companion that could destabilize orbits. And here's the kicker. Some of these factors might be detectable before we even find planets. For example, stars with unusually low lithium abundance, like our Sun, may be more likely to host rocky planets. Others show subtle brightness variations that hint at hidden Earth-sized planets. The field is moving fast, and in the next decade, we'll go from guessing to predicting which stars are most likely to harbor life. And that's exactly what we'll explore next. The hidden signatures that reveal a star's potential to host another Earth.
So, if sun-like stars are the real sweet spot for life, that means we've been misled by red dwarfs for decades. But hold on, do all scientists actually agree with Kipping's solar hegemony idea? Or is this still a huge debate?
That's one of the most important questions. And the answer is no, not everyone agrees. In fact, this is one of the hottest debates in astrobiology right now. On one side, you have Kipping and a growing number of researchers who argue that red dwarfs are fundamentally hostile to complex life. On the other, you have teams like those at the University of Washington's Virtual Planetary Laboratory, who insist that life is far more resilient than we assume, and the planets around red dwarfs could still harbor biospheres, even if they look nothing like Earth's. The disagreement isn't just academic. It shapes where we point our telescopes, how we design missions, and even how we define habitability itself. Let's break down the two main camps. The solar hegemony camp, led by Kipping, says that the combination of tidal locking, extreme flaring, atmospheric erosion, and poor photosynthetic potential makes red dwarf planets evolutionary dead ends for anything beyond microbes. They point to the lack of atmospheric detections by JWST, the high-energy radiation environments, and the statistical paradox of why we don't orbit an M-dwarf if they're so common. Their conclusion? Complex life requires stable, long-term surface conditions, something only G and K-type stars reliably provide. But the red dwarf resilience camp counters with several compelling arguments. First, they say we're being Earth-centric. Just because our life needs visible light, oxygen, and liquid water on the surface doesn't mean alien biochemistries couldn't thrive under infrared light or in subsurface oceans. Europa and Enceladus show that life doesn't need sunlight at all. It can run on geothermal energy. Second, they argue that strong planetary magnetic fields or thick initial atmospheres could shield against flares. A 2023 study in the Astrophysical Journal modeled a super-Earth with a powerful dynamo and found it could retain its atmosphere for billions of years, even around an active red dwarf. Third, they note that flare activity decreases dramatically after the first billion years. So if life emerges after that violent phase, it might have a stable window to evolve.
Okay, so it's not black and white, but where's the evidence tipping the scale? Has JWST settled this yet?
Not yet, but it's getting close. In early 2025, JWST observed the TRAPPIST-1 system with its mid-infrared instrument, MIRI, searching for thermal emission signatures that would indicate atmospheres. The results? Planets B, C, and D, despite being in or near the habitable zone, showed no detectable heat redistribution. That strongly suggests they lack thick atmospheres. If they had global winds or greenhouse gases, the dayside heat would spread to the night side, creating a measurable signal. But the data showed extreme temperature contrasts, consistent with bare rock or thin, transient atmospheres. That's a major blow to the resilience camp. And then there's Proxima Centauri b. In 2024, the extremely large telescope in Chile, using high-resolution spectroscopy, detected no oxygen, water vapor, or methane in its spectrum, even during quiet stellar periods. Remember, this planet gets blasted by X-ray fluxes 400 times stronger than Earth receives from the Sun. Models now suggest that even if it started with an Earth-like atmosphere, it would lose it in under 100 million years. That's far too fast for complex life to emerge. But here's where it gets really controversial. Some scientists, like Dr. Lisa Kaltenegger at Cornell, argue we're missing a key possibility: cloud feedback. She proposes that thick cloud cover on the day side of tidally locked planets could reflect enough starlight to cool the surface and stabilize liquid water. Her climate models show that under the right conditions, a red dwarf planet could maintain a habitable eyeball zone, a ring of liquid water between the scorching day side and frozen night side. It's a fascinating idea, but so far, there's no observational evidence to support it. JWST hasn't seen the cloud signature she predicts.
So it's still a debate, but the data is leaning towards kipping.
Increasingly, yes. And there's another layer most people don't talk about: the timescale problem. Even if a red dwarf planet survives the early flare phase and develops life, the star's extreme longevity might work against the evolution of intelligence. Think about it. If a star lives for 1 trillion years, why would intelligence arise in the first 10 billion years? Statistically, civilizations should appear much later, when the universe is far older. Yet here we are, early in cosmic history. Kipping calls this the temporal fine-tuning problem. The only way to resolve it is if stars with lifespans of 5 to 15 billion years, like our Sun, are the only ones that can produce observers. That's not just speculation, it's a testable prediction. And now, remember that green glow mystery from the cold open? The one about alien skies? Well, here's the twist. If red dwarf systems are sterile, then any civilization that looks up at the night sky will see mostly yellow and white stars, not red ones, because they'll always be orbiting a sun-like star themselves. That means the red sky paradox isn't a paradox at all. It's a selection effect. We don't see a red sky because observers can't exist under red skies. It's a profound realization. Our perception of the cosmos is filtered by the conditions that allowed us to evolve.
That's mind-bending. So the universe looks the way it does because only certain stars can produce eyes to see it.
Exactly. It's a form of cosmic self-consistency. And this is why the debate matters so much. If Kipping is right, then SETI should stop listening to red dwarfs and focus exclusively on G and K-type stars within 100 light-years. Missions like NASA's upcoming Habitable Worlds Observatory should prioritize imaging planets around stars like 82 Eridani or HD 40307, not TRAPPIST-1. And philosophically, it suggests that Earth isn't a fluke, it's a template. But what if we're wrong? What if we ignore red dwarfs and miss the one system where life did find a way? That's always a risk, and good science keeps an open mind. But resources are limited. We can't study every star equally. So we follow the probabilities. And right now, the odds strongly favor solar hegemony. Still, the final word isn't in. Over the next decade, JWST, the ELT, and the Nancy Grace Ruhmann Space Telescope will analyze dozens more exoplanet atmospheres. If they find even one red dwarf planet with biosignatures, like oxygen and methane in disequilibrium, the resilience camp wins. But if they keep coming up empty, then Kipping's view becomes the new standard.
So this isn't just about stars, it's about how we define life, intelligence, and our place in the universe.
Exactly. And that brings us to the biggest question of all. What does this mean for humanity's future? If sun-like stars are rare cradles of life, then Earth might be one of the first of its kind, or one of the few. That changes how we think about our responsibility, our search for others, and even our long-term survival. Because if complex life is confined to a narrow stellar window, then protecting it, here and potentially elsewhere, becomes the ultimate cosmic imperative. And that's exactly what we'll explore next: the legacy of solar hegemony and what it means for the future of life in the galaxy.
So if sun-like stars are truly the only viable cradles for complex life, what does that mean for us? Not just as scientists, but as a species. Are we alone? Or are we part of something bigger?
That's the ultimate question, and it's where science, philosophy, and even ethics begin to converge. If David Kipping's solar homogeny model holds, then Earth isn't a statistical fluke. It's a representative of a rare but real cosmic pattern. In a galaxy of 200 billion stars, maybe only 20 billion fall into that ideal mass range of 0.74 to 1.6 solar masses. And of those, only a fraction will have stable planetary systems, protective gas giants, metal-rich compositions, and calm galactic neighborhoods. But even if just 0.1% of those systems host an Earth 2.0, that's still 20 million potentially inhabited worlds. So no, we're almost certainly not alone, but we might be part of a very exclusive club. And here's the profound implication. Complex life may be cosmically synchronized. Because stars in Kipping's range live 5 to 15 billion years, civilizations that arise around them will tend to emerge within a similar cosmic window, roughly between 8 and 12 billion years after the Big Bang. That's exactly when we're living. So if there are other intelligent species out there, they're likely at a comparable stage of development, not millions of years ahead or behind. That changes everything about how we think about contact. It suggests the galaxy might be filled with civilizations just now waking up, looking outward, asking the same questions we are. We're not late to the party. We're right on time. But this also carries a warning. If complex life is confined to this narrow stellar window, then Earth might be among the first of its kind, or one of the few. The universe is only 13.8 billion years old. Many sun-like stars are still young. Others haven't even formed yet. So if we're early in the cosmic timeline for observers, that means we have a unique responsibility to protect this fragile experiment called life, not just for ourselves, but possibly for the entire future of intelligence in the Milky Way. Because if we fail, if we destroy our biosphere or our civilization collapses, there may not be another chance for billions of years. That's not poetic exaggeration, it's a direct consequence of stellar astrophysics.
That's heavy but also empowering. So instead of feeling small in a vast universe, we should feel significant?
Exactly. For decades, the Copernican principle told us we're ordinary, just another planet around just another star. But Kipping's work flips that on its head. We're not ordinary. We're optimized. Our star's mass, our planet's distance, our system's architecture, all of it aligns with the conditions that maximize the probability of complex life. That doesn't mean we're chosen. It means we're the product of a rare convergence of physical laws that allow observers to exist. And that makes Earth not just precious, but possibly pivotal. And this is already shaping the future of space exploration. NASA's upcoming Habitable Worlds Observatory, scheduled for launch in the late 2030s, is being designed specifically to image Earth-like planets around G and K-type stars. It won't waste time on red dwarfs. Instead, it'll target systems like 82 Eridani, HD 4037, and Tau Ceti, stars that fit Kipping's criteria. The goal? To detect biosignatures like oxygen, methane, and water vapor in their atmospheres. If even one of those systems shows signs of life, it confirms that solar homogeny isn't just a theory, it's a universal rule. Meanwhile, the Square Kilometer Array, set to come online in the late 2020s, will scan the skies for radio signals, but now with a refined strategy. Instead of listening to thousands of red dwarfs, SETI teams are shifting focus to the 200 or so sun-like stars within 100 light-years. Why? Because if intelligence requires stable long-term surface conditions, then those are the only places it can arise. It's a more targeted, more efficient search, and if Kipping is right, it's the only search that matters.
But what if we find nothing? What if after decades of looking at sun-like stars, we still see silence?
Then we face an even deeper truth. We might be the first, not just in our galaxy, but in the observable universe. Remember, the conditions for complex life didn't even exist until several billion years after the Big Bang. Heavy elements from supernovae had to seed the cosmos, stable planetary systems had to form, and only then could life begin its slow climb. So if we're alone right now, it's not because the universe is hostile, it's because we're pioneers. And that makes our survival not just a human concern, but a cosmic imperative. Think about it. Every time we protect a rainforest, reduce carbon emissions, or preserve biodiversity, we're not just saving Earth, we're safeguarding the only known instance of complex life in a galaxy that may be mostly sterile. And if we one day build self-sustaining colonies on Mars or beyond, we're not just expanding humanity, we're ensuring that the flame of consciousness doesn't go out. Because if solar homogeny is real, then life like ours is vanishingly rare, and that rarity is our greatest responsibility.
So this isn't just about astronomy anymore, it's about meaning, about purpose. Precisely. Science often gets accused of making the universe feel cold and indifferent, but this does the opposite. It tells us that our existence is not random, that the laws of physics conspired over billions of years to create a world where eyes could look up at the stars and minds could ask, why are we here? And the answer may be, because only in places like this can such questions even be asked. And that brings us full circle to the red sky paradox. Why don't we see a red sky? Because observers can't exist under red skies. The very fact that we see a yellow-white sun tells us something fundamental about the universe. It's structured in a way that allows complexity to arise, but only under very specific conditions. We're not anomalies, we're evidence. And that means every telescope we build, every mission we launch, every child who looks up at the night sky, they're all part of a grand cosmic story that's just beginning to unfold. So what's next? Do we keep searching?
Absolutely. In fact, the next decade will be decisive. JWST is already ruling out red dwarf habitability. The ELT will soon analyze atmospheres in unprecedented detail, and within 15 years, the Habitable Worlds Observatory could deliver the first true image of another Earth. If it finds biosignatures, we'll know we're not alone. If it finds silence, we'll know how rare we are. Either way, we'll have an answer.
And if we do find another Earth, what then?
Then we'll know that life is not a one-time miracle. It's a cosmic pattern. And that pattern points to stars like ours, not the most common, but the most capable. So we'll keep looking. We'll listen. We'll explore. Because now we know where to look. Not in the crimson glow of red dwarfs, but in the golden light of stars like our sun.
Final thought. After all this, do you think Earth is special?
Not special in the sense of being unique, but special in the sense of being representative. We're not a fluke. We're a template. And that means somewhere out there, under another sun-like star, there's another world with oceans, forests, and maybe even someone asking the same question. Are we alone? And if we're lucky, if we're wise, we'll find each other.
If you've made it this far, thank you. This journey from red dwarf flares to cosmic responsibility has been mind-blowing.
And if this changed how you see the place in the universe, hit subscribe. We go deep every episode. Drop a like if your perspective shifted, even a little. And comment below, do you think we're alone or part of a silent cosmic network, just waiting to connect?
We read every single comment.
Until next time, keep looking up. The answers are out there.